Is this on? Okay, thank you. Hi, good morning, everyone. I'm Yohei Onuki from Japan. I officially belong to a Kyushu University in Japan, but since 2 years ago, I'm staying in France. I also belong to ENS region. And here I talk about the breaking of internal waves parametrically excited by ageostrophic anticyclonic instability. This study is collaborated with Sylvain Jobot and Thierry Doxor at ENS region. So the target of this study is ocean surface scale. As you know, the motions of order 1 to 10 kilometers in the horizontal direction is called the surface scale. And this surface scale is characterized by the situation velocity number is around 1. And this corresponds to the transition range between the large scale two-dimensional geostrophic flow field to the three-dimensional waves and small scale turbulence. And this surface scale includes various physical processes, such as the development of frontal or filament structures or vertical motions, and also the instability of some motions, such as the convective instability, centrifugal instability, inertial instability, or symmetric instability, barometric instability. But today, we talk about more minor, less known process named the ageostrophic anticyclonic instability. This ageostrophic anticyclonic instability, or AAI, occurs when the low speed number is around 1 in an anticyclonic flow field. This instability is similar to the famous inertial instability, but this AAI occurs for a more broad range of situations, even when the vertical vorticity is not greater than the frequency this instability occurs. And this AI is further classified into some categories, such as the instability of coastal current, instability of baroclinic jets, or instability of elliptic vortex. And today I talk about this final one, the instability of elliptic vortex. As for the this instability, previous studies via some linear stability analysis or asymptotic analysis to get the instability growth rate. But the nonlinear evolution of this process and the final breaking mechanism of internal waves have not been investigated. Then in this study, we investigate the breaking of internal waves generated by this AAI using a numerical simulation. Okay, this is the concept of a model. We cut that a small domain from an anticyclonic surface scale Eddy, and we rotate and distort the model domain with time, and observe the instability in this numerical model. And this lower panel schematically explains the mechanism of this instability. We consider a small initial rectangular domain in the anticyclonic eddy. And with time, the angle of this domain rotates while being advected by the background vortex. And if the shape of the vortex is elliptic shape, so the shape of the domain varies while being distorted, then we consider plane wave disturbance in this domain. The rotation, the angle of the angle and the magnitude of this wave vector varies with time because the wave frequency is determined by the length of the wave number. The wave frequency varies with time, and if this variation of the wave number and the rotation rate matches, parametric resonance occurs, so the wave disturbance amplified exponentially. This is details of our model formulation. We consider Busnescu fluid on the left plane, and we decompose the variables into the reference state and disturbance component. The reference state is a linear stratification and a homogeneous elliptic vortex. And we introduce a time-dependent Fourier transform for the disturbance component, different from the usual Fourier transform. Now, the wave vector k varies with time because of the straining of the background vortex. Then the governing equation in Fourier space is written in this form. Now we have not assumed any infinitesimal disturbance. We include the nonlinear interaction terms here. Okay. The energy equation for this system is written in this form. Now the kinetic energy is produced via the shear production term, the interaction with the background vortex via the time t. And this kinetic energy is converted to available potential energy through the term c. And these two types of energies are dissipated through the terms epsilon u and epsilon theta. And this equation also involves the nonlinear transfer terms and also the energy flux in wave number space because of the change in the wave vector. When we neglect nonlinear terms and viscous terms, all the wave number components are decoupled. So the system can be written by these ordinary differential equations. In this system, the potential vorticity is invariant. So based on this potential vorticity, we can define the vertical mode and also the wave mode as a residual of this vertical mode. And the point here is that because the wave vector k and l are no longer stationary, the vertical mode varies with time. And the energy budget for the wave mode and vertical modes are written in this form. Now the wave mode energy is produced via the shear production term. And also wave mode energy is produced by the forcing from the vertical mode disturbance. And the vertical mode energy also varies with time because the wave number varies. In this way, the energy production rate is decomposed into three components. And for this system, we can also apply the linear stability analysis. So here the equation system is written in this form. Now the coefficient matrix is a function of time and it varies with periodically with time. Therefore, we can apply the Floquet theory to derive the instability growth rate as a function of these parameters. Yeah, E is the ellipticity of the vortex, and Rossby number is now defined based on the vorticity of the vortex and also divided by the Coriolis parameter. And this phi is the initial angle of the wave vector against the horizontal direction. And these are the results of linear analysis. Actually, this result is almost identical to the previous ones. The point here is that the instability growth rate depends on the Rossby number in this form. When Rossby number is small, this instability growth rate is very small, exponentially small. And this scaling is explained by the asymptotic analysis by previous studies. Okay. And this instability is important when Rossby number is close to 1. This is the configuration of our nonlinear simulations. As I explained in this model, we rotate the model shape with time periodically, so following the background vortex. And we use the Fourier method. So in Fourier space, each point rotates around the vertical axis. Okay. Now the domain shape is tuned such that the largest mode, so the largest wavelength mode grows the fastest. And this angle or the aspect ratio of the model domain is determined based on the linear stability analysis. And we carried out experiments with around 58 parameter ranges. But I explain mainly for the two cases. The difference between these two conditions is the instability growth rate. We first explain the situation, Rossby number is 1, so the growth rate is large. And the next, Rossby number is 0.9, growth rate is small. First, this is the case when Rossby number is 1 and the growth rate is large. Here I'm showing the density structure at the surface of the model domain. And this black curve is the streamline of the background vortex. So we can see undulation pattern of the isopic null surface because of the amplification of internal gravity waves. And this internal wave will soon break to make a small scale turbulent state in this form. In the left upper panel, I'm showing the time series of the energy density. So first energy is exponentially amplified and it will reach some saturation level. And the next panel is the energy dissipation rate. At the time of energy saturation, this, because wave breaking occurs, energy dissipation rate is suddenly enhanced to a much higher level. And the lower panel is energy spectra for the free turbulent state. We can see some column graph isotropic spectra for high wave number region. Next, this is a result Rossby number is a bit small, so the instability is weak. Also, in this case, the wave energy is exponentially amplified at the initial stage, but after it is saturated, it gradually decreased to much lower level, and also energy dissipation rate decreased in the long-term limit. And this right panel, the snapshot of the signal surfaces. So different from the previous strong instability case, the large scale density over terms cannot be seen. So instead, we can see some high horizontal wave number disturbances. So the state velocity field gradually shift to that free turbulent state, but we can see direct wave breaking. To explain the mechanism of this transition to the turbulence, so we did a frequency analysis of the energy spectrum. So this left panel shows the time series of the frequency spectrum of the kinetic energy and the wave potential energy. As the initial stage of the simulation, we can see energy concentration at a particular frequency, which is the rotation rate of the vortex. But gradually, this energy is redistributed to other frequencies. And we can see a pair of frequency energy accumulation at a pair of frequencies. And in the actually, so these two frequencies correspond to 0.4 and 0.6 of the vortex rotation rate. The sum of these two frequencies coincide with the frequency of the initial unstable mode. And this is a signature of the parametric subharmonic instability. So in this simulation, the initial wave the energy of the initial wave disturbance is transferred in frequency space through the resonant triad interaction. And finally, most of the energy is concentrated at the local inertial frequency, and the spectrum shape is close to the usual Garrett-Munk spectrum. Now we move on to more quantitative discussions. Now we aim at finding the scaling relationship between the energy dissipation rate and the external parameter. Specifically, we consider the instability growth rate lambda. This is estimated from linear stability analysis. And we non-dimensionalize this energy dissipation rate using the Osmito-Frank scale and also the vertical wave number of the primary unstable wave. And we also scale this instability growth rate lambda by the buoyancy frequency n. And this panel is a scatter plot against lambda over n and this eta or MP. So we can find the two types of scaling relationship exist depending on the range of the instability growth rate lambda. When instability is weak, this eta or MP is roughly proportional to lambda over n. But if the eta MP is if the lambda over n is large, this eta MP is roughly proportional to the square root of the lambda over n. In terms of the energy dissipation rate, this epsilon u is when instability is weak, this epsilon u is proportional to the square of the instability growth rate. But when instability is strong, this epsilon u is proportional to the growth rate. Now we try to explain why these two types of scaling exist. For this purpose, we define the time scale of the energy variations. In this system, the primary unstable wave energy is supplied from the vortex, and it will be further transferred to the smaller scale and will be dissipated. Then the energy growth time scale of this unstable mode is defined in terms of the growth rate model. On the other hand, the energy decay time scale of this primary unstable wave is defined using the energy level EP and also energy dissipation rate epsilon U. And from the simulation data, we identify that these two time scales are comparable throughout all the experiments. Okay. Next, we define the fluid number of the unstable wave that is defined in this form. And when the instability is weak, we expect that from the weak turbulence theory, the energy transfer, energy decay time scale should be proportional to the FRP minus 2. On the other hand, if the instability is strong because direct wave breaking occurs, this FRP should be around 1. And from these two considerations, we expect that this fluid number should have two types of dependence, scaling dependence on the middle. And actually, the simulation results are consistent with this expectation. And combining these two scaling estimates, we can reasonably explain why this epsilon U has two types of scaling dependence on the lambda. Finally, I explained the contribution from the vertical mode. And we decompose the simulation data into the wave mode and the vertical mode and compare the energy levels. This scatter plot shows the energy levels, wave energy, and vertical mode energy. And throughout the experiments, vertical mode energy is no greater than 20% of the wave mode energy. So the system is almost governed by the wave mode. And we also decompose the energy production rate into these three terms and compare them in this middle panel. This red triangle is the energy production rate, direct energy injection to the wave mode. And the blue square is the energy production wave mode assisted by the vertical mode. And this cyan cross is a direct energy injection to the vertical mode. And then this energy injection to the vertical mode is almost negligible in the simulation. Therefore, vertical mode energy is produced via the nonlinear interaction, the dissipation processes. On the other hand, when we compare these two terms, the wave mode energy produced assisted by the vertical mode is explained up to 30% of the total energy production rate. And this effect that the energy production wave mode assisted by a vertical mode is much more important when this ellipticity with the background vortex is large. This is a summary of our study. In this study, we investigate the breaking process of internal gravity waves, parametrically excited via ageostrophic anticyclonic instability using a numerical simulation. And we identify two different scenarios of wave breaking, depending on the instability growth rate. And depending on these breaking scenarios, we found that two types of scaling relationship exists for the energy dissipation rate. And this study is now submitted to JPO and under review. Okay, that's all. Thank you.